All right, section 11, so this is 6.11, is on independence. Okay, and so independence is probably just what you think that it would be. It's if you have multiple events and none of the events depend on anything, or they don't depend on each other, then that would mean that the events are independent. For example, if I flip a coin twice, I can't flip a coin twice with just one event, right? I have to flip a coin, and then I have to flip another coin. I guess technically I could flip two coins at the same time, but the second time I flip the coin has nothing to do with the first time that I flipped the coin. They're independent, right? Just because I get a heads the first time doesn't mean I'm more likely to get a heads or tails the second time. So that means that the events are independent. The probability that it's going to rain today and we're going to have chicken in the cafeteria. Well, those two events are independent, right? The rain has nothing to do with the chicken that they're cooking in the cafeteria. So events are independent if they do not rely on each other. And so the formula for the probability of A given B, if the two events are independent, is simply the probability of A. Or the probability of B given A, if the two events are independent. A has nothing to do with B, right? They're independent events. So that would just be equal to the probability of B. Now, if the events depend on each other, then that's different. All right? So, we talked a little bit, we were using Venn diagrams in another section, and we said that events were mutually exclusive, or they had disjointedness. And so that is kind of related to an independent event or a dependent event, in a way, I guess. All right. Now, the next rule we're going to go over for two independent events is the probability of A union with B if the two events are independent. So that would be, or this isn't union, I'm sorry, intersected with B. That would be like this here. If we had an event A and an event B, the part where they intersect, okay, if the two events are independent, then we just say the probability of A times the probability of B. All right. So here's an example that the book gives on this multiplication rule for independent events. It says a coin is flipped, a die is rolled, and a jack of clubs, and a card is drawn. I got a little bit ahead of myself. A coin is flipped, a die is rolled, and a card is drawn from a deck. Find the probability of getting a tail on the coin, a 5 on the die, and a jack of clubs from the deck of cards. So none of these events depend on the other. They're all independent events. So the probability, let's call the coin event, the flipping of the coin, let's let that be event A. Let's let event B be rolling the die, and let's let the card, drawing the card, be event C. Okay, so we want to know the probability of flipping a coin and getting a tail. So I'll call a coin as tails. Intersected with the probability, it says, of getting a 5. So we'll say rolling the die and getting a 5 really is what it is. Intersected with the probability of getting a jack of clubs. So since each one of those is independent, we simply take each probability and multiply it times the next probability. So the probability of getting a tail, a 5 on the die, and a jack of clubs from the deck of cards is going to be what? Let's see. The probability of getting a tail when you flip is 1 out of 2. Right? It's either going to be heads or tails. The probability of rolling a die and getting a 5, on a standard die there are 6 sides. So that's going to be 1/6. And then the probability of drawing a jack of clubs, there are 52 cards in a deck of cards, right? So a jack of clubs is only one of those cards. So that would be 1 out of 52. Alright, so that's 1 over 12 times 52. So 1 out of 624 times. And that's about, let's see, 0.0016. That's a small probability. Not super small, not like lottery small, but that's like 1 out of 624 times. If you did those 3 events, that would happen. All right. What makes 6.12 so complicated is the concept of counting. Different ways to count the number of ways that something can occur. For example, if I wanted to take a group of 2 students out of this class, how many ways could I do that? Or, if we all went down to the football field and we had a race, how many different ways could the students in this class finish first, second, and third? So things like that, how many ways things can happen, that is counting. The fundamental rule for counting is that, let's see, E sub 1, it says, is an event with N sub 1 possible outcomes. E sub 2 is an event with N sub 2 possible outcomes. The number of ways the events can occur in sequence is N sub 1 times N sub 2. This principle can be applied for any number of events occurring in sequence. All right. That is the fundamental rule of counting. The example, your book gives a lot of examples, but one example your book gives, it says, a local office supply store offers ballpoint pens from 3 different manufacturers. Each manufacturer's pen come in either red, blue, black, or green, and either fine or medium tip is available for each color. How many different pens does the store carry? All right. So we have different colored pens, and then each pen can come in either fine or medium tip. So the way that we could figure out how many that the store carry says it also says that we have 3 different manufacturers. So 3 manufacturers, and then each pen comes in red, blue, black, or green, and then each tip is either fine or medium. So we have 3 manufacturers. Each of those have 4 pens, and each pen can have one of 2 tips on it. So that means 3 times 4 times 2, there are 24 different pens. Okay. All right, this is a pretty classic question. I've seen this question, this counting question, asked in a variety of ways, but it just makes you think a little bit. It says you have a stack of 5 textbooks. English, history, statistics, of course, geology, and psychology. How many ways can you arrange these textbooks on a shelf? All right, so we're going to arrange those textbooks on a shelf, and we have 5 different places that we're going to put those textbooks. Okay? When I choose one textbook, I have 5 to choose from. So there's 5 possible ways to choose the first textbook. Well, after I've already placed that textbook, then I only have 4 to choose from the second time. The next time I have 3, the next time I have 2, and then the last time I only have 1. So the possible number of ways to arrange 5 textbooks comes out to be 5 times 4 times 3 times 2 times 1. 20 times 6, that's 120. So there are 120 ways that you can arrange those 5 textbooks. Okay, that, not this problem, but this calculation that we just did, 5 times 4 times 3 times 2 times 1, counting down like that and multiplying, has a special name. It's called factorial. All right, and so 5 with an exclamation point behind it, that means 5 factorial. So 5 factorial is 5 times 4 times 3 times 2 times 1. So any number factorial is going to be the product of all of the numbers less than or equal to that number down to 1. So 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay? And so we have to use factorials to help us do other types of calculations, other types of counting calculations. The official definition in general terms, factorial, n factorial is equal to n times n minus 1 times n minus 2, and then you keep multiplying until you get to 1. So I'd say times 3 times 2 times 1. Also, by definition, to get all formulas to work out, 0 factorial is defined as 1. Even though 0 factorial, 0, there are no positive numbers less than 0. To get all formulas to work out, you get 1 for 0 factorial. So if you've ever used a calculator and seen that little exclamation point, that's what it means.
So it's the largest number or the first number, or I'm confused about how you choose what?
Oh, it really it depends on the problem, but let me get into how we use it, and maybe it'll make a little bit more sense. All right, so one type of problem or counting problem that we run into is the number of ways that you can order objects or choose objects. Okay? If we're worried about order, then that's called a permutation. Okay? So a permutation is a specific order for arrangement of objects in a set. All right. For example, I told you earlier, if we all went down to the football field and we all started racing and we wanted to know how many ways that we could come in first, second, and third place. Well, order would matter. You know, maybe you get first place or second place or third place. So it matters as far as what place you get. You know, if I got first, you got second, and somebody else got third, that would be a different outcome from if somebody else got first, you got second, and I got third. Those are different outcomes. So does order matter when races, you know, when you're racing and things like that? Yes, order matters. The formula that we use for permutations, there's two ways I've seen this written. Actually, three ways. I've seen this written like this, where you have N, P, K. I've also seen an R here instead of a K. I've seen this written as N, P, R. They mean the same thing. K and R just stand for the same thing. N is the total number of items. K or R here, that's the number of items that are being chosen. So NPK is one way to write that. Your book writes it like this. It means the same thing. If you look at it in a calculator, in a Texas Instruments calculator, it's like this here, NPR. Again, means the same thing. So a permutation is equal to n factorial divided by n minus k factorial. Okay. So what type of counting problem will we use this with? I made a reference to a race. Here's a race problem here. Says 7 sprinters have advanced to the final heat at a track meet. How many ways can they finish first, second, and third? So, how many sprinters do we have? We have 7, right? So n is going to be equal to 7. Now that's just the number of sprinters. That's not n factorial, that's just n. Now, how many places are we looking at? First, second, and third place. Okay, so our k is going to be equal to 3. So this can be written, like I said, a couple of different ways. One way is 7p3. Your book writes this as a p with a 3 at the bottom and a 7 at the top. It's just a different way to write it. If we apply that to our permutation formula, that would be 7 factorial divided by 7 minus 3 factorial. So that's 7 factorial divided by 4 factorial. So in a race, order matters. So that's why we have to use a permutation. Now, if I want to calculate this, that would be 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1. But let me show you something. Let me show you a way to help save you some time when you're calculating factorials or permutations. 7 factorial is 7 times 6 times 5 times 4, and then it's times 3 times 2 times 1. But you can stop at any number and put the factorial sign after it, and then do not write a number after it, right? So I can count this down to 4 factorial, and you say, why would you want to do that? Because my denominator has a 4 factorial. And so if I'm working these out by hand, and you ever have a fraction, if you count down the numerator to the factorial in the denominator, then those cancel out because of the way that multiplication and division work. So this calculation is 7 times 6 times 5. So if you were doing this out by hand, it's a lot easier to do 7 times 6 times 5. All right, so that's 210. So if I had 7 sprinters, there's 210 ways that those 7 sprinters could place first, second, and third in a race. All right. Whenever you have duplicated objects or items, so we wouldn't be talking about people because you can't duplicate people, right? But let's say that we had a big group of books and some of them were the same, but we were still wanting to know how many ways could we arrange those books. Then you have to use a different formula, and it is one for distinguishable permutations. And that formula is n factorial divided by n sub 1 factorial times n sub 2 factorial times n sub 3 factorial, so on and so forth to n sub k factorial. Okay, and so all of these in the denominator, the numerator of course is the total number of items factorial. The numbers in the denominator, let's say I had 3 history books that were the same, then this would be 3 factorial. Then I had 2 English books that were the same, then the next would be 2 factorial. And then all of my other books are different. Well, if they're all different, all these others are 1 factorial, so they don't make a difference. But if we have objects that are the same, and you want to know how many ways you can arrange those objects, you say the total number of objects factorial divided by, anytime you repeat something, you divide it by that number factorial. So let's say, how many ways could we arrange the word, say, Mississippi? So how many ways could we arrange the letters in the word Mississippi? All right, so first we need to know how many total letters are in Mississippi. So count all the letters. All right, I got 11. So our numerator is going to be 11 factorial divided by, all right, how many or which letters are repeated? We need to see, are any of the letters repeated? Of course they are. That's why we chose this word. There's only one M. So you don't have to put a 1 factorial in the denominator. That wouldn't do anything, but you can if you want to. How many I's are there? 4, right? So you divide by 4 factorial. How many S's are there? 4. Divide again by 4 factorial. How many p's are there? 2. Divide by 2 factorial. Now, you can't simply multiply factorials together. For example, 4 factorial times 4 factorial is not equal to 16 factorial. So you do have to expand these. One way, 11 factorial is a pretty big number if you think about it. But one way to give me just a few less calculations if I was doing this by hand is just to write this out to 4 factorial. Because one of the numbers in the denominator is a 4 factorial. And so I could cancel one of these 4 factorials out. So I still have to figure out what that numerator is equal to. It's 11 times 10 times 9 times 8 times 7 times 6 times 5. Alright, so I get 1,663,200. And then the denominator is going to be 4 times 3 times 2 times 1 times 2 times 1. Right? 4 factorial times 2 factorial. So that is 24 times 2, 48. Right? So it's going to be that number divided by 48. And I should get a whole number when I do this because of the way that the permutations work out. I'm not going to get a fraction. I'm going to get a whole number, no decimal. So 34,650. There are 34,650 distinguishable ways that we can arrange the letters in Mississippi. Yes.
Why would you not put M?
Because there's only one M. So if there is only one M, you could put a 1 factorial down here, but dividing by 1 factorial is simply just dividing by 1. So we didn't use the M because it wasn't repeated. All right. Now, another type of counting is combinations. So we looked at a type of problem where order mattered. That was a permutation, like those racers, those sprinters. But what if order doesn't matter? So combinations is a type of problem or counting problem where order does not matter. We run into this a lot of times if we're choosing objects or choosing items. For example, if I wanted to choose a group of 3 people in this class, then if I choose, say, John, Sally, and Jeff in that order, or if I choose Sally, Jeff, and then John in that order, that's still the same group. So the order that which I choose them doesn't matter. That's a combination. So if you're choosing objects from a group and order doesn't matter, that's a combination. Like if I just wanted to randomly assign, let's say that we started our own club and we had president and vice president, then, and I randomly assigned that to two people, and they really didn't have any meaning. Maybe they were going to be our leaders, but, you know, assigning president to one and vice president to the other, or vice president to one or president to the other, if I choose those two people, there's two different ways that I can choose those two people. You know, I can choose Jack and then Jill, or I can choose Jill and then Jack. I have the same two people. So when you're choosing objects like that and order doesn't matter, it's called a combination. And I don't know why I misspelled that. I put an extra letter in there. All right. Now the formula for combinations, again, the way that I usually see this written is NCR, and that's the way that the Texas Instrument calculators have it. But you can have NCK. It means the same thing. Or your book, it writes your C, your K at the bottom, and your N at the top. But that formula is very similar to the permutations formula. It's just a little different. It's n factorial divided by n minus k factorial times k factorial. So you can see we're dividing by an extra factorial in the denominator. So combinations will always be less than permutations. I would say less than or equal to permutations. All right, here's an example about the lottery. Of course, to win something like the Powerball, you have a better chance of being hit by a meteor or struck by lightning twice. But some of the smaller lotteries you actually, could win if you were lucky enough. I read an article that showed, I think it was 2 different people that had won 2 lotteries of a couple million or more. So those people were really, really lucky. Or who knows, maybe they shouldn't have won. Maybe it made them into a different person. Anyway, this problem says, in South Carolina's Carolina 5 lottery, a player selects 5 different numbers, so 5 different numbers from 1 to 36. Inclusive, meaning you can choose 1, you can choose 36. If the numbers selected match the player's numbers in any order, the player wins. So with the lottery, you don't have to have the numbers in order. It would be nobody would ever win. There'd be very few lottery winners if order mattered. Okay? If you've ever seen a Powerball ticket or bought a Powerball ticket or something, it's almost impossible to win that, but it's even more impossible to get them in the same order that they're chosen. Okay, so this is a combination. We have 36 different numbers to choose from. How many are we choosing? 5, right? So the combination is, it's 36 C5, like that. Or the way your book would write that is C sub 5, got a superscript or an exponent here that kind of looks like 36. It's not really an exponent, but it's written in that place. All right, so that would be 36 factorial divided by 36 minus 5 factorial times how many are we choosing? 5. So it's times 5 factorial. Now, in most calculators, if you just try to find 36 factorial, it's going to probably give you a scientific notation answer because that number is so big. So, let's see. I don't know if my little simple calculator here has a factorial button. I don't see. Am I right? Yeah, there it is. So you can see even this calculator that has about 3 times as many places or 2 times as many places as normal calculators writes this as 3.71, basically 3.72 times 10 to the 41st power. Alright, well, probably don't want to write in that answer as your numerator. But what we can do, let's simplify the numerator. So that's going to be 36 factorial over 31 factorial times 5 factorial. Now, let's simplify the way that I showed you earlier. So count down the numerator. This is 36 times 35 times 34 times 33 times 32 times, I'm not going to go all the way because what? I'm going to stop at 31 factorial because that is one of the numbers in the denominator. And so my 31 factorials will cancel out like that. So now I'm just left with this, which is still a big number, divided by 5 factorial. Okay, so 36 times 35 times 34 times 33 times 32 equals, that's still a pretty big number, 45,239,040 divided by 5 factorial. 5 factorial is what? That's going to be 120. So this is going to end up being 45,239,040 divided by 120. And we better get a whole number. Alright, so I got 376,992. 376,992. So what that means is, if I was to purchase one of these lottery tickets and go in there and write down my 5 different numbers that were between 1 and 36 inclusive, then there are 376,992 ways that I could select those numbers. Now, part B is interesting. It says, what is the probability of winning? Alright, so the probability of winning, there's only one correct set of numbers out of that many types of numbers. So it's going to be 1 divided by 376,992. So you can see it has to write this as scientific notation because it's so small. It was times 10 to the negative 6. So I'd put 5 zeros 0.00000, and then 265. I'll leave it there. 265. Really small probability. You know, if you think about that as a percentage, that's still 0.000265%. It'd probably be about the same probability as me walking across campus and finding $1 on the ground. You know, just that doesn't happen, right? Nobody's going to leave money on the ground. Yeah, in the book they rounded to 3, but it's rounded. I put my little squiggly marks here, so I'm good. All right, there is a little table that is in your book, but everything in the table is basically on your formula sheet. It just kind of summarizes these different rules. Telling if a problem is a permutation or a combination is going to depend on whether order matters or order doesn't matter. Okay? If order matters, then it's a permutation. If order does not matter, it's a combination. So, I guess an easy way you could remember that would be if you can just kind of associate combination with lottery ticket, then the order that you choose the numbers on your lottery ticket doesn't matter. That's a combination. For those of you who maybe don't have a calculator, you can use Excel to do a lot of this. So you might want to look at the next section. It kind of tells you a little bit on how to do that. Also, in your book, throughout, it shows you how to find combinations in your book. See, this right here is a combination, 36, and then you select that NCR that's under probability, which I believe is under math. Yeah, because look, it says 36 math, select probability, choose NCR, and then 5 and hit enter. It does it for you. Okay, so of course the TI calculators, they do a lot.